Hello guys. In fact, in our previous session, we have presented the control system, the main components of this control system, which are mainly the controller, the plan, the sensor, and we have presented also the mathematical tools that are needed in order to do these calculations, mainly the Laplace transform and the inverse Laplace transform, in order to go from time domain to frequency domain and vice versa, as well as the Taylor development in order to linearize a nonlinear system. So this topic will be mainly concentrated on the modeling of a system. What do we mean by modeling? It is mainly to present different types. In fact, the outline of this presentation will be as follows. First, I'll present the Laplace transform and the inverse Laplace transform. In fact, I will not go through this part as it was presented in the previous session. Then I'll go through the transfer function representation, which is in the frequency domain, then through the modeling, and in fact we will focus mainly on two different models, the mechanical one, the electrical one, and finally we'll go through the state space. In fact, for the first one, the transfer function it is in the frequency domain, in the Laplace domain, in the S domain, whereas for the modeling, the state space representation, they are mainly in the time domain, function of t. And at the end of this presentation, I'll go through the block reduction in order to show the main Mesa rules to be used in order to simplify a block diagram in order to get at the end one block between the input and the output. So I'll skip. The tensor function, in fact, it is the function that algebraically relates a system's output to its input. In fact, we have a relation between the output and the input. So as it's clear, it is one output and one input. So mainly a tensor function is a link between one input, one output only. So if we have more than one input, we'll see later on what to do. The function will allow separation of the input, the system, and the output into three separate and distinct parts, unlike the differential equations. And it's one of the main advantages of this representation. In fact, we can access through each of the blocks of the system, whereas for the differential equation, it is modeling of the whole system or the whole process in one equation. So the main advantage of the tensor function is to represent the ratio without determining the input, which is not the case for the time domain systems. In fact, in the time domain, we need to know what is the type of inputs in order to get the output. So we say that it's a response for a step input. It is a response for a ramp input. Whereas for the tensor function, no, it is a ratio of the output over the input. I do not need to know what is the input type in order to determine the system characteristics. So the conditions to have a real system, as we have presented before, is that we have to have a linear system. A linear system is not to have a real system, but to be able to study the tensor function. Because if the system is not linear, we cannot study a tensor function. So we have to linearize it first. We must have a time invariant system, which is if we apply an input alpha to a system at a time t0 and we apply the same input at a time t1, at a time t2, at a time t beta, we have to get the same output of the system. In fact, this is not really the case if we are applying it with time frame, with very long time frames, years for example, because the mechanical or the electrical system characteristics and operation will degrade, but we will consider that the test will be achieved in a small period of time, and at the end the system must be causal, which means that the output at instant t depends mainly on the input at instance t minus 1, t minus 2, t minus 3. So Going from a characteristic equation, the one which is shown in the first row, doing the Laplace transform of this characteristic equation while considering the initial conditions as being null, then we can go to present the transfer function, which is C of S over R of S. C of S is considered as being the output and R of S as being the input. Of course, to have the system uh, real, we must have n at least bigger or equal to m. So n must be bigger. So going back to any system, it can be presented by these three blocks: the basic systems, of course, the controller, the process, and the feedback, which could be the sensor, in fact. From the system, we can calculate three different transfer functions: the feed forward, the open loop, and the closed loop. The feed forward, it is the relation between the output y of t and the error input. So we can express it as y of s over epsilon of s being equal to g of s times c of s. As for the open loop, it is like doing the process but once. So the output will be yd. In fact, there is an error at this level. I'll correct it directly. This it is as being y d of s over epsilon. Excuse me. Only one input active at a time. So to calculate y r of s, we will have r of s different than 0 and l of s equals to 0. Whereas to calculate y l of s, we will have l of s equal different than 0, whereas r of s equal to 0. Getting to the example, in fact, at this level we have three different inputs: the input or reference, the disturbance 1, and the disturbance 2. So the output will be the combination of these three inputs together. Okay, after representing the tensor function, we'll go through the modeling phase. In fact, in the modeling phase, we can model a system, represent the output function of the input in three different ways: the time domain characteristic equation, which we know well from high school. For example, for the pendulum, it is theta double dot plus tan theta of t equals 3 u of t. We can also represent it in the frequency domain using the tensor function, the one we have presented earlier. So from the characteristic equation, we can apply the Laplace transform and get the frequency domain. And also we are able to present it using the state space representation that will be showing later on in this presentation. Let's start by defining what is a modeling. First of all, the model is a relation between the observed signals, mainly the input and the output signals. As for the types, we have the mental models, the graphical models, mainly the mathematical models, and the software models. Of course, we'll be focusing on the mathematical model, and to build a model, we can go through these subsystems, mainly regrouping each subsystem alone, then grouping them together to form a full model of the system. And we can also go through identification. In fact, here I want to go back to the first chapter, as I have said before. In fact, we have three different types of systems or types of identification of the system. It is the black box, the one that we don't have any idea of the input of the components of the system. So we just insert some inputs and read the outputs, and then we do the identification. Also, we have the gray box and the white box where we know some physical phenomena or all the physical phenomena of the system, and mainly will be concentrated on these two types of systems. So for the electrical model first, the main electrical components are the RLC. So here you can see that the R mainly will be focusing on the frequency domain because of the presence of the derivative and the integration. So based on the Laplace transform, a derivative is expressed by 1 over S, whereas the integration is expressed by S. So in fact for the capacitor it is 1 over C times S. S is a plus operator. For the resistor it is only R. As for the inductance it is Ls. At this level we can do the modeling using two main approaches, the mesh current or the node voltage approaches. So for example in this case, for this example we want to calculate the transfer function between the output Vc of t function of the input V of t. So we want to find the link between both variables. Here is the complete calculations. First, we apply the mesh current. In fact, V of t equals L di over dt plus Ri plus 1 over c integral of I dt. This can lead, in fact, to the following formula after several modifications, or we can first go from this formula, the first one that I have presented, to its Laplace equivalent. So it is Lsi of s plus Ri of s plus 1 over Csi of s equal V of s, and you all know that Vc of s here is equal to 1 over Cs times I of s. So we'll have two equations. We can extract I of s from the second one and insert Vc of s in the first one, so that we can get this relation, and at the end we'll be able to model the system output, which is Vc of s over input, which is V of s, as follows. Here is another example. At this level, we have two different nodes, two different meshes. Excuse me, two different meshes will express each mesh alone, and based on that, we'll be able to calculate the I2 of s function of V of s. In fact, it is for the instructor to precise which variables he needs to extract or to express. So you may be asked to express Vc of s function of V of s, or let's say Vc of s function of I1 of s, but in this case it's V of s function of Y2 of s. Here are some clues for the solution. In fact, I have included the final solution, not detailed, but you can write the whole solution alone. Okay, after presenting the electrical modeling, we'll go through the mechanical modeling. In fact, for the mechanical systems, we have three different components: the spring, the damper or the dashpot, and the mass. And each one is presented as that. For the spring, it is a linear relations so it's K. For the damper, it is Fv times S as Laplace transform, and for the mass, it's M times S squared. And for the mechanical level,